Are we recording? We're already going? Alrighty. Hello everyone, and welcome to our lesson on the origins of modern astronomy. Now, as I'm sure you all know, astronomy is a field of science that goes back thousands of years, and in that time it has changed a lot. Our understanding of the universe has changed a lot. So in the next 45 or 50 minutes, I'm going to try to explain to you some of the early ideas that people had about the stars and the sun and the planets, and how those ideas have changed over time as our ability to observe the stars has gotten better and better. Of course, people have been looking at the stars for thousands of years all over the world, in cultures all over the world. However, in this lesson, we're mainly going to talk about the ancient Greeks. Starting on slide 5, we have a bit of information about the ancient Greeks and their school of astronomy. Here we have a basic definition. You can read along with me. Astronomy is the science that studies the universe. It includes the observation and interpretation of celestial bodies and phenomena. Celestial just means in the sky. Celestial bodies would be things like planets and stars. Phenomena would be things we see happening in the sky. What we see things do. What are those planets and stars actually doing? Because they're not just sitting there, that's for sure. The Greeks used philosophical arguments to explain these phenomena. They also used observational data. On the next slide, number 6, we see an example of what's called an astrolabe. Now, an astrolabe is a tool that, again, people have been using for thousands of years, and not just the Greeks, but also Persians, Arabs, Chinese, Indians. Many different cultures had different types of astrolabes. And as they traded with each other and shared their ideas and their information about the stars, they were able to make better and better astrolabes. An astrolabe is really like a set of wheels, almost like a set of gears that turn within each other, like the gears in a watch. And as they can turn, they show the position of the stars and the sun and the moon and different planets at different times during the year. So just like the hands of a watch show the time during the day, an astrolabe can be turned to show the position of the stars throughout the year. If you look at this picture, you see that astrolabe has two main circles. We have the main body and then that smaller circle on the inside. And if you look at the top of that circle, you'll see a small triangle, like a small arrow. It's, let me get my pointer, right here. Now, if you were using this astrolabe, you would point that arrow at the date. If if you can look around that outer circle, you can see a lot of writing. Those would be the months and the days of the year. So someone who wanted to use this astrolabe would turn that inner wheel, this inner wheel here, until this arrow pointed to the correct date. Then this circle on the inside would show them where the stars were going to appear. Also, you can see here inside that circle there are a lot of faint lines. These lines here that I'm highlighting would show the paths of different stars and planets throughout the night. Notice, if you get to the very center of that circle, you see a point where there's no movement in the very center. We're going to talk about that a little bit later in the lesson, that point in the sky where there's no movement. But for now, let's move on to the next slide. Number 7. Calculating Earth's circumference. Now you may know from your lesson in geography that circumference refers to the distance around a circle. We know the circumference of a circle, we use that old formula 2 pi r, 2 times pi times the radius, to calculate the circumference of a circle. This picture on slide 7 shows you a really brilliant experiment that was devised by a Greek astronomer named Eratosthenes. Eratosthenes realized that as you went closer to the equator, down here, the shadows of objects became smaller and smaller. And that's because the sun was higher in the sky. And Eratosthenes realized that he could measure the length of different shadows at different points on the Earth and use those shadows to figure out the actual size of the Earth. So to understand that, let's look at the map and the globe pictures there. Notice the map up here in the upper right shows us 2 cities, Alexandria at the mouth of the Nile River in Egypt, and Syene farther to the south near the modern day area of Aswan. Here, in the globe picture on the lower left, we can see a post that he put at Alexandria. Obviously, it was not this big. And the well at Syene. Now, people already knew that this well at Syene, this deep, narrow hole for finding water, this well was very special because people knew that on June 21st, sunlight would go all the way down to the bottom of the well. But during other times of the year, the sunlight would never reach the bottom. Now the reason is that Syene sits on the Tropic of Cancer. So on June 21st, you can see from the picture, the sun's rays on June 21st are coming straight at Syene. The sun is directly overhead at noon on June 21st. And so sunlight goes straight down all the way to the bottom of the well. Now, Eratosthenes realized that if he put a giant post at Alexandria, he could measure the length of the shadow, and from that angle, from the length of the shadow, he could calculate the angle of the sun. Here, I'll draw you a picture of that. So here's my rather crude picture. Eratosthenes realized that with this post at Alexandria, right down here, would still throw a shadow to the north at noon. And he realized that if he measured the height of the post and the length of the shadow, he could calculate this angle. And he calculated that angle to be 7 degrees. So he realized that the difference between Syene to Alexandria, that distance covered a 7-degree angle on the surface of the Earth. Now remember that a circle is 360 degrees. So 7 degrees is about 1/50th of a circle. So Eratosthenes realized that the distance from Alexandria to Syene, from the post at Alexandria to the well in Syene, was 1/50th of the way around the Earth. And from that, he was able to calculate the circumference of the Earth. And he actually did a really good job of doing it. He got to within about, I don't remember the exact figure, but he was only off by about 1 or 2%. He was very close. And it's always so amazing to me to think that Eratosthenes had this correct, and still in the West we went backwards, so that 1,000 years later there were many people in Europe who thought that the Earth was flat. They didn't even realize the Earth was round, where Eratosthenes 1,000 years earlier had figured out not only that the world was round, but he'd figured out exactly how big it was. Even Christopher Columbus, who came about 2,000 years after Eratosthenes, thought that the Earth was much smaller. He thought he could go around the world because he thought the Earth was much smaller. So it's almost like from Eratosthenes to Christopher Columbus, in 2,000 years, we went backwards in our understanding. So Eratosthenes, a very, very clever man who figured out the size of the Earth just from looking at shadows. Here, 2 different models of the solar system. We see them on the next slide. And if you'll give me just a moment. There are pictures of these on slide 9. So if you want to look at slide 9, we see 2 different models for the universe. On the left side, that picture on the left shows the geocentric model. Remember, we've seen that word geo before in studies like geography, geology. Geo just means earth. Centric, center. So geocentric means earth at the center. And if you look at that picture on slide 9, you will notice we have the earth here at the center of the universe, with everything, all the different planets and stars moving around the Earth. The second model that we see on the right is the heliocentric model. Helios is the ancient Greek name for the sun. So, if geocentric means Earth at the center, heliocentric means the sun at the center. And there's a great picture of that over on the right. We can see the sun at the center with the Earth in 4 different positions, and then that circle on the outside here are the signs of the zodiac. So the geocentric and heliocentric models. The ancient Greeks, the Ptolemaic system. The ancient Greek astronomer Ptolemy created a model of the universe that accounted for the movement of the planets. And I think we may be... okay. The ancient Greeks believed in that geocentric model, the one that's there on the left, with the Earth at the center of everything. They believed that the Earth was the center of the universe, and then outside the Earth, you had these different planets moving around. You had Venus, and then Mercury, and then the Sun, and then Mars, that the Sun and the planets all moved around the Earth. Now, there were big problems with that model when they actually looked at the paths that these planets took across the sky. Remember what we learned at the beginning of the presentation. The Greeks believed in observation. So when they observed the planets moving across the sky, they found that the idea of the Earth being at the center, it had problems. You can see an example on slide 11 with what we call retrograde motion. Notice at number 1, when Earth is at number 1, Mars is going to be directly overhead Mars is going to be at its highest point at about 5 in the morning, early morning. At 2, Mars is going to reach its highest point a little bit earlier, maybe 2 or 3 in the morning. At number 3, notice Mars will reach its highest point late at night, closer to midnight, maybe like 1 in the morning. But overall, look at the overall pattern. As the Earth moves past Mars, we get this strange effect where Mars seems to stop, move backwards, and then continue on its path. Now, I know this is difficult to understand. It's really hard to wrap your head around this just from one picture. One thing I do want you to understand, when you look at this, realize that this path of Mars, we're not talking about Mars's path during one night. We're talking about the path that it takes over 6 or 7 months. So even though during one night we would see Mars move from east to west like that, Mars is going to make that same path across the sky every night. But we're talking about how that arch is moving from month to month. Another thing to understand about this, we're not talking about the path at the same time every night. We're looking at that path that Mars is making. That's the highest point in Mars's path through the night. I know hearing this for the first time, it's really hard to understand retrograde motion, but there are a lot of great pictures and videos to help people understand this. If you go to YouTube and do a search for a video on retrograde motion, you'll find great resources showing you how Mars moves across the sky from day to day and from month to month. But the point is that retrograde motion makes no sense if the Earth is at the center of the solar system. If the Earth is at the center, there's no reason for there to be retrograde motion. I want to skip ahead just a little bit. Let's look at slide 18. Here on slide 18 we have three pictures. The picture there on the left shows you that model that Ptolemy came up with. He has the picture there of the Earth, Venus, and the Sun. To understand the retrograde motion of planets like Venus and Mars, he had to insert these small circular orbits inside the orbit. He said that yes, Venus moves across the sky from east to west, just like the Sun, but within that orbit it also circles, so that sometimes it comes back and moves from west to east, right here on the bottom part of the circle. So let's go back now to slide 11 and continue where we were. Well, here we go, on 12. Nicholas Copernicus. He was an Italian living in the early 1500s, so about 500 years ago. Copernicus concluded that the Earth is a planet, and he proposed a model of the solar system with the Sun at the center. So it was Copernicus who proposed a model like the heliocentric model that we saw earlier in the presentation. Let's move on. Tycho Brahe. Tycho Brahe was about 50 years or 40 years after Copernicus. So he would have grown up as a boy who was interested in science. He would have grown up reading about Copernicus, and maybe Copernicus would have been like his science hero. Just like I remember when I was really young, the big science hero was Stephen Hawking, and science nerds wanted to be like Stephen Hawking. So for Tycho Brahe, that would have been Nicholas Copernicus. He would have admired Copernicus. Tycho Brahe designed and built instruments to measure the locations of heavenly bodies. He was a great telescope designer and builder. And he had a great observatory where he would measure the light from different stars and the shadows from that light to get a precise idea of how they were moving across the sky. Tycho Brahe's observations, especially of Mars, were more precise than any made previously. Yeah, keep in mind, they didn't have the Hubble Space Telescope back then. Uh, they didn't have the advanced lenses that we have today. They didn't have, X-ray telescopes. They had very, very simple devices, and they had to make them themselves. They couldn't order them from a catalog. So it was very difficult and very time-consuming work. But Tycho Brahe was one of the best who came of the generation after Copernicus. Kepler. Kepler was like the next generation of astronomers. So Tycho Brahe would have been his hero. And Kepler was a German. Kepler was very brilliant, and he discovered 3 laws of planetary motion. First, he realized that Copernicus and Brahe were correct when they said that the sun was at the center of the solar system and the Earth moved around the sun. But let's go back to that picture that we saw on slide 9. That picture of the sun and the Earth's moving around the sun, we still have a circular orbit. The Earth is moving in a circle around the sun, as if there were a piece of string connecting the sun and the Earth. And the Earth always stayed at the end of that string. Imagine taking a small, like a ball, like a yo-yo at the end of a string, and swinging it around. That yo-yo would move in a circular pattern. And people like Copernicus and Brahe, they thought that that's what the Earth did. So they were right that the sun was at the center, but they were wrong about the shape of the Earth's path around the sun. Kepler, coming about 50 years later, in the early 1600s, he realized that the orbits of the planets were elliptical, and that the sun was at one focus of the ellipse. So it was not a circle with the sun at the center. They were an ellipse, like an oval, with the sun at one focus. He also realized that the planets revolve around the sun at varying speed, which means they don't have the same velocity. It's not like that yo-yo that I'm spinning around. It's moving in a circle, and it's always moving at the same speed. Kepler realized that both of these ideas are wrong. The paths of the planets are ellipses, and those planets speed up and slow down. You can see a good illustration of this on slide 16. Notice, this picture shows you one revolution of the planet Earth as it moves around the sun. And notice that when the sun is farthest from the sun, when the Earth is farthest from the sun, over here on the right, it's moving very slowly. But as it gets closer to the sun over here, it moves faster. So if you keep an eye on the red dot, and my cursor seems to be broken here. Hey Mike, do you know what's wrong with my cursor? I think the mouse just cropped out. You do not know? I don't know. Well, I can't teach this without the mouse because I can't go from slide to slide. Alright, we can cut this out anyway. It may just be a dead battery. That would be my guess. Hello? Hello? Hey, got a technical difficulty here. The mouse is not working. I think it may just be a dead battery.
Yes, I think so.
I know these battery-powered, the battery-powered mouse, they go through batteries very quickly.
This time you refer and
Oh.
I will go out to buy the new one.
Oh, I thought I saw a pack of batteries. Do they take double A?
Yes.
They do? Okay, good. All right, and I'll add a cut note in there so we know when to start up again. And cut. Notice here, when the Earth is closer to the sun, it's moving faster, but when the Earth is farther from the sun, it's moving slower. So that path of the Earth around the sun might be something like this. As we come closer, we move faster and faster and faster, and then over here on the right, we slow down. We get to our slowest, and then we speed up again, faster, 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 slower, 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 slower. It's almost like throwing a ball up in the air and catching it. If you throw a ball up in the air, straight up, it's going to be moving fastest just as it leaves your hand, and then it's going to slow down and come back to your hand. You throw it up again, it's going to slow down and come back. The movement of the Earth around the sun is very similar. It's moving fastest when it's close to the sun and slowest when it's far from the sun. So we go up and fall back. It's almost as if the Earth is falling around the sun. One thing that always surprises students when they see this picture is that the Earth is actually closer to the sun in January and December, and it's farthest from the sun in July and June, because at least where I live, in America, December and January are the cold months, and July and June and August are the hot months. So we would think, wait a minute, shouldn't the Earth be closer in July and August and be farther in December and January? The answer is that the temperature of Earth, the weather on Earth, has more to do with the angle of the Earth's orbit to its rotation. It has more to do with the angle than the distance, because this drawing is very exaggerated. In this drawing, it looks as though the Earth is maybe twice as far in July and August. That's actually not quite correct. It's exaggerated so you can understand it, but the orbit of the Earth is actually closer to a circle than this picture. All right, let's go back a step to slide 15. Kepler realized that the orbits were ellipses. An ellipse is an oval-shaped path. From these measurements, we came up with the astronomical unit, which we abbreviate AU. It is the average distance between the Earth and the Sun, which is about 150 million kilometers. When we measure distances like the distance from the sun to other planets in our solar system, like Jupiter, Saturn, Uranus, Neptune, we usually use the astronomical unit. Like we might say Mars is 2 or 1.5 astronomical units from the sun. Jupiter is 4 or 5 astronomical units from the sun. Saturn is 8 astronomical units from the sun, and so on. But once we get outside of the solar system and we start talking about the distance to other stars, we don't use astronomical unit anymore. We start to use light years. All right, let's move on. The next person we're going to talk about, Galileo. Galileo was actually before Kepler. He was around the same time as Tycho Brahe. But he was, like Copernicus, an Italian. So I guess for Galileo, Copernicus really would have been his hero. Galileo is very famous for proving that Copernicus was right about the Earth revolving around the sun, and the sun being at the center of the solar system. He's also very famous because when he proved this, his ideas came up against the teachings of the church at the time, and he wanted to prove to the church that he was right, and the leaders of the church would refuse to even look in his telescope. Like, they would not look because they accused him of rigging the telescope to make them look foolish. But in the end, they ended up looking foolish, and everyone knows now that Galileo was correct. His most important contributions, in addition to proving Copernicus right, were his descriptions of the behavior of moving objects. He developed his own telescope and made important discoveries. First, he discovered the moons of Jupiter. So he discovered that these other planets moving around the sun, they had smaller bodies moving around them, just like our own moon. He realized that the planets were disks, really were spheres, not just points of light. Like, he was able to look at the surface of Venus and Mars and actually draw maps of these planets. He was able to see different features on the surface of Venus and Mars. No one had ever been able to do that before. He also realized that Venus has phases just like the moon, and we're going to see that in the next couple slides. He realized that the moon's surface is not smooth, and we're going to see that later in the presentation. And he realized that the sun had sunspots or dark regions. And he did a lot of drawings of the sun with these dark sunspots. He did not know what they were. He could not explain them. Today we understand them a lot better, and we'll get into those in later lessons. But here on the next slide, number 18, we have that Ptolemaic model of the universe on the left, with Venus moving in a circle within its orbit, so we have the retrograde motion. Then in the middle, we have that the Copernican model with the Earth moving around the sun and Venus moving around the sun inside the Earth. And there on the right, we see different phases of Venus. And if you look at that picture in the middle, you can get an understanding of how those phases work. You can see Venus is going to have a light side and a dark side, depending on where the sun's light is hitting. So when Venus is on the far side, and so the sun is between the Earth and Venus, then we would get that circular image, like right here. Now, of course, we never see this without a telescope, because we can't see Venus during the day because we have the sunlight during the day. It's too bright for us to see the light of Venus. We really only see Venus in these phases right here, here and here, because those are the only times when there's a straight line between the Earth and Venus without sunlight getting in the way. So the images like this one, the circle, we can only see with a telescope. Now, if we look at Venus without a telescope, it looks like a little dot of light. But Galileo proved that when we see Venus, when we look at it with a very excellent telescope, we see something more like this. Right, let's move on. And those are the phases of Venus moving around the sun, just like we see the phases of the moon as they move around the Earth. But let's move on. Isaac Newton. We're moving on here. Remember, Tycho Brahe and Galileo were late 1500s. Kepler was early 1600s. Isaac Newton was in the late 1600s. So maybe another 50 years. People like Copernicus and Galileo and Kepler were very bright and very smart in figuring out the fact that the sun was at the center of the universe and that the planets moved around the sun, and that they moved around the sun in elliptical orbits. But they could not explain why. They could not explain why the planets moved around the sun. Why not just move in straight lines? Why did the planets move around the sun at all? Isaac Newton gave us the next piece of the puzzle there. There's that, when we think of Isaac Newton, he's the man under the apple tree. The famous picture of Newton is he's sitting under an apple tree and he's looking at the moon and he's wondering, why does the moon revolve around the Earth? And why does the Earth revolve around the sun? And then the apple falls and it hits him on the head, and he said, oh, the apple fell because of gravity. And then he realizes, oh, the same force that pulls the apple to the Earth is the force that holds the moon in orbit around the Earth and the Earth in orbit around the sun. So Isaac Newton was the one that put gravity into the picture. Here we see on slide 19, although others had theorized the existence of a gravitational force, Newton was the first to formulate and test the law of universal gravitation. This means that the greater the distance, the less the force, and the greater the mass, the greater the force. The two objects that are close together will have a strong force. Two objects that are far apart will have a weak force. Two small objects will have a weak force, but two large objects will have a strong force. And from the model of Kepler and this new idea of gravity that Newton added, we were able to get a picture like the one on slide 20. Gravity's influence on the orbits of the planet. Notice at the top of the picture we have that little gray planet. Those arrows from the planet to the sun show you the effect of the sun's gravity. The sun's gravity is pulling the Earth in towards the sun. But that straight line here that goes out to the right shows you the tendency of the planet without the influence of gravity. So that's the planet's momentum. That's the path. Well, here. Well, this is the path that the planet would take without gravity. So this force here kind of bends that path and then bends it again and again and again, and that's why we have this net motion here of A and B. That's the momentum, that linear momentum affected by that gravitational force between the planet and the sun. Okay, moving on, 22.2, the Earth, Moon, Sun system. We're going to talk about three types of motion that the Earth is undergoing. The two main motions are rotation and revolution. Rotation, let's see if I've got something I can demonstrate this with. I'll just use my coffee cup for now. That's the Earth moving around like this on its axis. And this is what causes day and night. So the Earth rotates one time in a day. However, as it's rotating, the Earth is also moving in that elliptical pattern around the sun. And one revolution, as we know, is 1 year. So one rotation is 1 day. One revolution makes 1 year. So from 12 o'clock to 12 o'clock, from January, February, March, April, May, June, July, August, September, October, November, December, January. Rotation and revolution. The third type is called precession. And there's a good example of this, a good illustration on slide 29. We're going to talk a little bit more in detail about it, but I want you to take a look right now, just so you know what we're talking about. Imagine if we take a top and we spin the top around. It's going like this, very quickly. That's just like the rotation of the Earth. Now, if you've ever seen a top spin, you know that as the top slows down, it starts to wobble back and forth. And then finally it topples over. Well, the Earth is doing the same thing. You can see here, it's spinning around. Well, you can see here, it's spinning around, but it's also wobbling back and forth. Now this wobble is very, very slow. We're going to talk a little bit now about just how slow that wobble is. So let's go back. All right. Slide 22, we see a great picture of Stonehenge, an ancient observatory. It's a big ring of rocks with other rocks placed outside. And if you stand at the middle, you can see the sun will rise and set over the rocks on certain days of the year. You can see here, we have a rock right here with the sun. I believe the sun is setting here. And I believe this is sunset on the equinox. So this is sort of like a giant calendar that people made. Okay, onward to the next slide. 23, motions of the Earth. Rotation. It's the spinning. There are two ways to measure rotation. Number one, the mean solar day is the time from one noon to the next, which is 24 hours. That's the day that we measure. That's the day that we know, from noon to noon. It takes 24 hours. But there's also another type of measurement called the sidereal day. And that's the time it takes for the Earth to make a 360-degree rotation. And that's with respect to a star other than the sun. And that's only 23 hours, 56 minutes, and 4 seconds. Now you might be saying, wait a minute, why are they different? Why is it that 360 degrees with respect to the sun is different from 360 degrees with respect to another star? There's an illustration of that on the next slide. You can see here, we've got the Earth and the sun. Notice it's not to scale. The Earth is not as big as the sun. It's much smaller. But look at these 2 points, X and Y. On day 1, X and Y are perfectly aligned with the sun. And so a line from the sun to the X and Y points out at some distant star. Like we might say out here, I don't know, Vega or any other star. But notice, after one day, the Earth has moved a little bit in its revolution, in its path around the sun. So notice now, if X and Y are going to point at the same star, they're going to point in the same direction, the Earth has not quite moved around an entire 360 degrees with respect to the sun, with respect to our sun. So here, after one day, from this point to this point, X has gone around one time. And we're back at the same point. But for it to be 24 hours, we would need to get to this point right here that's aligned with our sun. So that would be another, and it's going to take another 4 minutes for X to reach that point. So it's going to take another 4 minutes for it to be midnight again. So that's why we say a sidereal day is 4 minutes shorter than a solar day. The next type of movement, the next motion of the Earth, revolution. Revolution is the motion of a body such as a planet or a moon along a path around some point in space. That's the Earth moving around the sun. Two important terms to know there, perihelion and aphelion. Remember our picture of the Earth's journey around the sun? Perihelion is this point right here, where the Earth is closest to the sun, and aphelion would be this point out here when the Earth is farthest from the sun. So I'll just mark that here. For the P, and then A. Perihelion and aphelion. And remember, perihelion is going to occur sometime in January. Aphelion is going to be sometime in July. Earth's axis and the seasons. The plane of the ecliptic. This is an imaginary plane that connects our orbit with the celestial sphere. Because of the inclination of our axis to the plane of the ecliptic, the Earth has its yearly cycle of seasons. Let's take a look at that on the next slide, number 27. Notice we've got a picture there with the sun at the very center and the path of the Earth right here from December to like April, May, June, July, August, September, October, November, December. And I'll put a little arrow there so we know which direction the Earth is moving. But look at the bottom left, that picture of the Earth. We see that it's almost like there are two blades going through the Earth. That green blade, that green plane, is the plane of the ecliptic. Now that's the plane where most of the planets that are revolving around the sun are on that ecliptic, like Mercury, Venus, Earth, Mars. They're all revolving around the sun on that same plane. But notice, the plane of our equator is not the same. Our equator is not aligned with the ecliptic. It's almost as if the Earth is tilted to its own orbit around the sun. Now what that means is that there are parts of the year when the north hemisphere is pointed at the Earth, and that would be over here in June. You can see we're taking a closer look at the Earth in June when the northern hemisphere is pointed at the sun. But imagine if we took that Earth over here in December, the southern half of the Earth would be pointed more at the sun. So over here in June, the northern hemisphere has summer, and the southern hemisphere has winter. When the Earth is over here in December, the southern hemisphere is pointed at the sun, and it has summer, and the northern hemisphere is pointed away from the sun, and it has winter. That's why June and July are the hot months for the northern hemisphere, even though it's when the Earth is at aphelion and farthest away from the sun, because it's pointed towards the sun. Now remember, we talked about three forms of movement. We talked about rotation, we talked about revolution. That third one, precession, the very slow movement. Precession traces out a cone over a period of 26,000 years. So remember, we used the example of the top. The top spinning around very quickly. That's like the Earth rotating. That's what causes the night and day. However, just like a top that slows down and starts to wobble, well, the Earth also has a wobble like this. But it's wobbling very, very slowly, so that it takes 26,000 years for the Earth to wobble one time around. Here, the sun, okay, the precession. There, yeah, there's an example of that on slide 29. Right now, the Earth's axis of rotation points to the North Star, Polaris. That's why no matter what season it is, no matter what time of the year it is, no matter what time of day it is, the North Star is always due north. I don't know if you've ever seen a time-lapse photograph of the night sky. You can see pictures. You can do a Google image search on time-lapse night sky or time-lapse stars. And you can see the way that during the course of the night, over the night from like 6 p.m. to 6 a.m., the stars trace out these circular paths through the sky as the Earth rotates, and they make these very beautiful pictures. But there's always a point at the very center where nothing is moving, just like there's that point at the center of the astrolabe where nothing is moving. And that point is the North Star, Polaris. That's the one star in the sky that doesn't move. However, and that's because our axis of rotation is pointed directly at Polaris. However, the Earth is wobbling away from Polaris, so it won't be like that forever. In another 13,000 years, we'll be pointed at Vega. And in between, we won't really have a good North Star. So we're very lucky. Right now we have a star that helps us find due north. So sailors and mariners and navigators have been very lucky for the past 1,000 years that the North Star has been, or Polaris has been just in the correct place. But in another 2,000 or 3,000 years, that won't be the case. And then, of course, in another 13,000, we'll be pointed at Vega. Let's take another step back to slide 28. The Earth-Sun motion. The solar system speeds in the direction of the star Vega. The Sun is revolving around the galaxy. The Earth is presently approaching one of its nearest galactic neighbors, the great galaxy in Andromeda. That's the next galaxy outside of the Milky Way. Just like we had perihelion and aphelion, remember perihelion is where the Earth is close to the Sun. Aphelion is that point where the Earth, that point in June or July when the Earth is farthest from the Sun. We also have two more terms, perigee and apogee. Just like the Earth's orbit around the Sun is an ellipse, so is the Moon's orbit around the Earth. And just like perihelion is when the Earth is closest to the Sun, perigee is when the Moon is closest to the Earth. Apogee is when the Moon is farthest from the Earth. Next part of this lesson, the phases of the Moon. I think we're all familiar with the phases of the Moon. You know, some nights you go out and you look at the Moon and it's a perfect circle. Some nights you go out and it's like half a circle. Some nights it looks like a cookie that someone took a giant bite out of, and it's only a little crescent moon. Lunar phases are a result of the motion of the moon around the Earth and the sunlight that is reflected from its surface. There's a really good illustration of this on slide 32. Notice, here we've got a picture of the Earth at the center and the moon moving around the Earth. Remember, the moon takes 28 days to move around the Earth, or rather this cycle takes 28 days. And here we have rays from the sun, so the sun is off in this direction to the right. Notice, because the light is coming from this direction, the moon has a light side and a dark side. Here, in number 1, a person standing on the Earth can only see the dark side of the moon. Now, because it's dark, we can't see it. And because it's overhead during the day, the sunlight shines too brightly for us to see it. Just like we can't see stars during the day because the sunlight is too bright. We can't see the moon during the day because the light is too bright. So we don't see any moon. That's what we call a new moon. Notice, as the moon revolves around the Earth, we go from point 1 to point 2. Now, notice a person standing on the Earth is going to look up at the moon like this, and they're only going to see a small portion of light, a small part of the light side. Look at the 3 lines that I drew there. Here on the left is the dark side. Here on the right is the light side. That's why we see only a small sliver of moon at sunset. And notice we see that moon in the evening. But as the Earth continues to rotate, that moon would set in the west. It's going to follow the sun down. First the sun's going to go down, and then the moon is going to go down after it. Notice, in number 3, we see what's called the first quarter. Here we can see the moon directly overhead at sunset, and notice we see equal parts of the dark side and the light side. So we see a half moon. And again, as the Earth rotates in this direction, that moon is going to set in the west just like the sun. And this, we keep moving on here. Next, the gibbous moon. Notice we mostly see, it's like the opposite of a crescent moon. Here, with a crescent moon, we saw a lot of the dark side on the left and a little bit of the light side on the right. Here, we see a lot of the light side on the right and a little bit of the dark side on the left, and that's called a gibbous moon. Notice both of these, all of the moons over here, we call waxing. That word appears here and here, and we would also call this a waxing quarter moon. That just means getting bigger. The moon's going from the new moon to the full moon, so we call it waxing. When the moon is getting smaller, notice down here at the bottom, we say it's waning. So notice, if you see a crescent moon in the evening, you know, like up here at the top of the slide, a crescent moon in the evening, you know that the moon is waxing. It's getting bigger. If you see that crescent moon in the early morning, like down here at the bottom of the picture, you will know that the moon is waning and that soon we're going to have a new moon. The same goes for the quarter moons here. If you see a quarter moon at sunset, you know that the moon is over here and that it's waxing. If you see a quarter moon at sunrise, you'll know that the moon is over here. That's the third quarter, and it's waning. So if you know a little bit about this model, you can always get a picture in your mind of where the moon is on its path around the Earth just by looking at the shape of the moon and thinking about what time of night it is. So this is a very excellent picture to help you understand a little bit about why the moon makes the shapes it does. And it will always help you. Anytime you look up at the moon, you'll be able to understand a lot about what you're seeing. Remember what we learned about the Earth back on slide 24, when we talked about sidereal days and how that point X goes one time around the Earth, pointed at the same star, but it's not quite aligned with the sun yet. And it takes 24 hours to realign with the sun and go back to being midnight. But when you talk about aligning with the distant stars, that only takes 23 hours and 56 minutes. The same, as you can maybe understand, we have the same effect with the moon revolving around the Earth. We have what we call the synodic month and the sidereal month. The synodic month is based on the cycle of the phases. It lasts 29 1/2 days. The sidereal month is the true period of the moon's revolution, and it's 27 1/3 days. Just like the sidereal day is a little bit shorter than the day that we measure, the sidereal month is a little bit shorter than the month that we measure. The difference between the 2 days, the difference of 2 days between the synodic and sidereal cycles is due to the Earth-Moon system moving in an orbit around the sun. The moon's period of rotation about its axis and its revolution around the Earth are the same, 27 1/3 days. It causes the same lunar hemisphere to always face the Earth. There's an illustration of that on slide 35. Notice up at the top of the picture, we start with day 1. We're going to start with a new moon. Notice the dark side of the moon is facing the Earth, so we would not see anything. Here we've got the Earth moving around the sun like this, and the moon moving around the Earth. However, notice that, of course, the moon is not moving in a perfect circle. It's actually moving something like this. Yeah, it's moving in a path like that. Notice there on day 14 3/4 we see the full moon. At the bottom of the picture, notice right here, we've got day 27. I'm going to highlight that dark part of the moon again, the dark side of the moon. Day 27 1/3, That's when the Earth, the Moon, and a distant star would be aligned. That's one true revolution for the Earth, for the Moon. However, we measure it in relation to the Sun, so we see that happening every 29 days, and that's our synodic month. The synodic month. Okie dokie. Next, eclipses. An eclipse is just a time when the Earth, the Moon, and the Sun are perfectly aligned. When you could draw a straight line between the Earth, the Moon, and the Sun. A solar eclipse occurs when the Moon is directly between the Earth and the Sun. You can see that on the next slide, number 37. And so the shadow of the Moon falls on the Earth. Now, it's important to remember that the plane of the Earth's orbit is not perfectly aligned with the plane of the Moon's orbit. The Moon's orbit, sometimes it's like this, so that the Moon might be up here when we have a new moon. So that just because we have a new moon doesn't mean we have a solar eclipse. We only get a new moon when this plane of the Moon's orbit is aligned with the plane of the Earth's orbit around the Sun. So it only happens like twice a year. Okay. But when it does happen, you can see it throws a tiny shadow, which we call the umbra, onto the Earth, and that shadow moves across the surface of the Earth as the Earth rotates. And that's what we call the solar eclipse. Whoop. Uh-oh. Uh-oh. Hello? Oh, crap, dude. I think I closed the video. All right, we're back. Cut. Next on slide 38, you can see the other type of eclipse, a lunar eclipse. This is when the Moon moves into the shadow of the Earth. So with a solar eclipse, the Moon is between the Sun and the Earth. With a lunar eclipse, the Earth is between the Sun and the Moon. And when this happens, you can see the Moon go dark. And you can see from the picture that this is going to happen during a full moon when the light side of the Moon is facing the Earth. So we would normally see the Moon as a complete circle, a full moon, but because the Moon moves into the Earth's shadow, we'll see part of the Moon or all of the Moon go dark. And in that picture on slide 38, you can see the path of the Moon during a partial eclipse up here with part of the Moon dark, and then on the bottom, the path of the Moon during a total eclipse. and the entire moon going dark. A little bit about the surface of the moon. Remember, we learned that Galileo was the first person to describe the surface of the moon. When we look at it today, we see a lot of craters. A crater is the depression at the summit of a volcano or a depression produced by a meteorite impact. You can see a good example of one of those in the next picture. All those on slide 40, all those little circles are craters. And probably the easiest one to see is this white circle here called the Copernicus crater, which is in the middle of the Mare Imbrium, or the Sea of Rains. And we're going to talk a little bit about those seas in a little bit. Most craters were produced by the impact of rapidly moving debris, like meteorites, like meteorites. Here on Earth, we have an atmosphere. So when a meteoroid enters our atmosphere and becomes a meteor, most meteors burn up in our atmosphere. They do not hit Earth. And if they do, they're burned up to the point that they're very small by the time they hit. Remember, the moon, because it is so small, it has very little atmosphere. There's no air on the moon. So there's nothing to burn up those rocks out in outer space. So meteoroids are constantly slamming into the moon. And that's why the moon looks the way it does, covered in these impact craters. So craters produced by the impact of rapidly moving debris. Rays are any of a system of a bright elongated streaks, sometimes associated with a crater. Again, back on slide 40, you can see the Copernicus crater looks like it has a bunch of rays coming out in all directions. It almost looks like an explosion. And it is. Those rays are like lines of dust that were thrown in all directions from the impact. And there's an example of that on slide 41. You can see that meteorite impact, the force of compression, and then the rebound. This rebound, it's almost like an echo. If you go up to a high mountain, there's another mountain opposite, you can shout out, "Hello!" The sound wave from your mouth will go out, it will ripple through the air, it will hit that other mountain and then bounce back to you, so you'll hear, "Hello! Hello!" This rebound is the same thing. That compression causes a wave to move through the rock in the surface of the moon. Then it hits something harder, a lower level of the Earth. That compression wave bounces back, and when it reaches the surface, it pushes dust in all directions. And that's what you see in the bottom picture there on slide 41. The lunar surface made of highlands. Most of the lunar surface is made of densely pitted, light-colored areas known as highlands. Yeah, those areas that are like white, very light gray, they're kind of mountainous. They're high up. The other area, the darker areas, are what's called maria. And this is from the Latin word for sea. These are ancient beds of basaltic lava. Remember, if you've seen our lesson on geology, you know that basalt is an igneous rock. Remember, basalt is composed of a lot of different minerals like feldspar, as well as elements like iron. The the basalt on the moon is very similar to the basalt on the Earth, with the exception that it has a lot more iron than the basalt here on the moon. Overall has a lot more iron in its surface than the Earth. Okie dokie. Move on to later. So the Maria, the seas, are ancient beds of basaltic lava. And if we go back to the page, if you go back to slide 40, you can see the two main Maria on the Earth are the Mare Ibrium, which is known as the Sea of Rains, and the Mare Tranquillitatis, what we call the Sea of Tranquility in English. Of course, people have seen these spots for thousands of years and tried to guess at what they were. In European culture, people said it looks kind of like a face, with the Sea of Rains being like an eye. In Japanese culture, they say that it looks like two rabbits that are working to pound mochi, with the Sea of Rains being a rabbit on the left and the Sea of Tranquility being a rabbit on the right. So that's like the bedtime story that they tell people, that they tell kids in Japan. That the Sea of Rains is a rabbit, and the Sea of Tranquility is another rabbit. I'd like to skip now to slide 44. You can see an example of a lot of these different forms. At the top of the picture, you see the highlands. Those are going to be the light-colored areas. And then at the bottom of the picture, the mare, which are going to be the dark-colored areas. So this can give you an idea of what you're looking at when you see the light and dark areas of the moon. As for the history of the moon, well, people have tried to guess for many, many years why the moon is there in the first place. Why does the Earth have a moon? The most widely accepted model for the origin of the moon is that when the solar system was forming, a body about the size of Mars impacted the Earth. So this would have been about 4.5 billion years ago, before there was any life on Earth, in the very early days of the planet. There was a huge crash of two planets. Imagine a planet the size of Earth and a planet the size of Mars crashing into each other. How enormous this must have been. When they crashed, it threw debris in all directions. It was ejected into space, and much of this began orbiting around the Earth. You can see a picture of that on slide 46, so that for maybe millions of years, or even hundreds of millions of years, the Earth had a ring, much like the rings of Saturn or Uranus or Neptune, and over millions and millions and millions of years, that ring formed into the moon through a process that's known as accretion. Remember, Newton taught us about universal gravity. So all of those objects, all the little pieces moving around the Earth would be pulled into one another, and eventually, they would accrete into larger and larger bodies, and eventually you would have one large body that would sort of sweep out everything in its path. Everything would be pulled into this one sphere, this one ball, and that's what became the moon. All right then. So with that, let's go ahead and finish for today. Hopefully this lesson has given you a more detailed understanding about the relationship between the sun, the earth, and the moon. Thank you for your attention, and I will see you next time. All right.